The last video that we did dealt with banked curves with no friction at all. This time we are going to add friction into our banked curve. The nice part is we don't have to reinvent the idea of what a banked curve is, so we're going to get just kind of straight into the picture of what's going on. We have our incline like this. Here's our angle, and here is our lane. So we've got our car sitting this way. This is a back view of the car again. And maybe the center is over here. The center of our curve is over here. So we've got a radius of curvature. We are again looking for find the max safe speed. And while we are at it, find the minimum safe speed. Now, for no friction, there wasn't a difference between the maximum and the minimum. There was a safe speed. If we went too slow, we would slide right down into the middle of the cone. If we went too fast, we would have been just kind of pushed out to the outer edge. Neither of those is a case that we want. Now that we've got friction, we're going to have to mess with this a little bit. We're going to have separate safe speeds, a minimum and a maximum. So we're going to need coefficients of friction. Let's have a mu-s of 0.8 and a mu-k of 0.5. With any sort of a rolling situation, and we are rolling because a car is on tires, right? With any sort of a rolling situation, we do need to think about this a little bit, what kind of friction we're going to use. If this is my wheel, as the wheel turns, if I look at a specific spot on the wheel, that spot is going to come into contact with the ground. When that spot's here, it's in contact with the ground. So I'm going to call this a point of contact. That point of contact is not moving relative to the ground. I'm not taking my whole wheel like this. I'm not taking my whole wheel and sliding it and skidding. I don't have that. What I have is a spot that stays in the same spot relative to the ground. As the wheel continues to turn, that spot will lift up off the ground. So, all of that to say, when we are dealing with a situation of something rolling, we are looking at static friction, not kinetic friction. Kinetic friction, so for rolling, we want static. For skidding or slipping, we want kinetic friction. So static friction. Here's our car, and here's our ramp. And there's some angle of inclination in there. I'm going to start drawing some forces. I have a gravity force that points straight down. I'm going to again leave the mass of my car to be just a capital M. We can call this thing 10 degrees. And we're going to make our radius a little bit more realistic than last time. So let's make this thing 100 meters. Maybe not 100. Let's go 80 meters. Alright, I've got this mg force that points downward. I've got a normal force that points perpendicular to my ramp. And then I've got friction. So I will have two different situations. If I am going to find the maximum safe speed, if I'm going too fast, I'm going to be pushed upward, kind of out of the ramp, in which case my frictional force is going to have to point down this way to keep me from sliding to the outside of the ramp. So this is for the maximum speed. The center of my ramp, the center of my turn, is off to the right, so I'm going to need a flat coordinate axis. And there is my max speed free body diagram. I do recognize that I'm going to have an acceleration vector that points to the right. So now looking at this, I need to break my normal force into components. And I'm going to have to break my frictional force into components. So my normal force, this top one, is going to be an n sine theta. This one over here is going to be an n cos theta. And over here I'm going to have a friction static cos theta, friction static sine theta. And there is my free body diagram. Now to do the problem. First I'm going to look in my y direction. So the sum of forces in the y direction, I will have an n cos theta that goes up, n is an unknown. I have an mg that points down, and I also have an fs sine theta that points down. Together, all of that's equal to mass times acceleration in the y direction, and my acceleration in the y direction needs to be 0. So I have two unknowns in here, but I'm going to plug in a little bit. My static friction force, if I'm looking at that max speed, I'm looking at the threshold value. So I want Fs max, and that's going to be equal to mu s times the normal force. So I can put that in already. N cosine theta minus mg minus mu static normal force sine theta equals 0. I'm going to put just my n terms on the left and my non-n terms on the right. I will factor out the n. So there's my normal force. Now I'm going to look at my x direction. I'm not plugging in right now because I don't know the mass of my car, but I would really like it if that dropped out, and I suspect that it will. X direction. My sum of forces in x. I've got an n sine theta to the right, and I now know my n. And I have an fs cos theta to the right. Fs is mu sn, so plus mu sn, and then so all that part is just fs. I need fs cos theta, so times cos theta equals mass times acceleration in the x direction. My acceleration in the x direction is going to be a centripetal acceleration, and that's going to be a v squared over r. That's the only red letter in this whole thing. I'm going to have to do some plugging in, and I'm going to have to mess with this quite a bit, but that's okay. I will factor out the n on the left side first, because if I'm going to be putting this expression in for n, I would like to do it once instead of twice. So I have factored out the n, and now I'm going to plug it in. I'm taking this whole expression and plugging it in for my normal force. Still going. Mass drops out. That's good news. If I'm solving for v, I'm going to multiply both sides by r and then take a square root. So I will get that my v is going to be equal to, if I multiply by r, I'm going to have this gr, and then sine theta plus mu s cos theta all divided by cos theta minus mu s sine theta, all that underneath the square root. There is my maximum safe speed. And if I want to plug in values, I can. Sorry, this is a plus, but that works out to be 30.1 meters per second, which is about 67 miles per hour. That's pretty fast, so that banked curve really helped us out in this case. But we need to look at the minimum safe speed also. For the minimum safe speed, we're going to have a little bit different of a situation. We're going to have a free body diagram that has some similarities, but a big key difference. So we are going to look at a minimum speed now. Why is there a minimum speed? Because if this car were stationary, it would potentially just start sliding down the ramp, and that's not what we want. So what happens is our frictional force, static frictional force, is going to have to kind of just go away for a moment, and I'll be back. If this thing is going too slow, then the car will start to slide down the ramp, which means the static friction force is now going to be pointing up the ramp. We're going to now have to break that static friction force into two components. This side is an Fs sine theta. This side is an Fs cos theta. But everything else is going to stay the same. So we have just reversed the direction of our friction force. What does that mean? Well, we might be able to get away with something back here. And actually, we are able to. Because the friction force is reversing directions, and our friction force, our F static, we said was going to be equal, because we're looking at our maximum case, our F static was going to be equal to mu static times the normal force. To reverse this, all we really have to do, mathematically, is tack on a minus sign. So anywhere where I had a mu s, I can replace that with a negative mu s. So Fs, here's a mu s, that's going to become a negative mu s, so that becomes a plus. That's a plus, that's a plus, that's a plus. Mu s, so a minus, minus, plus. We're just flipping the signs on anything that has a mu s. Minus, plus, and now we're going to get a V min that is pretty easy to find. When I punch this in, I get an answer from my calculator that says 20.9 I, which is an imaginary number, right? If this is an imaginary number, that means that my minimum speed is really 0. There is no minimum speed for this particular setup. When this ramp is inclined at 10 degrees with a coefficient of static friction of 0.8, the car doesn't need to be moving, and it's just going to stay put on the incline anyway. If I had a sharper incline, if my angle instead of 10 degrees were 30 degrees and my coefficient of friction were lower, like maybe, I don't know, 0.4, maybe I'd get different results. Let me try that actually. If I change, so just for the sake of example, if I change my angle of incline to 30 degrees, this is really steep, and my mu static to 0.4, then I end up with a V minimum of 10.7 meters per second and a V maximum of 31.9 meters per second. I didn't change any equations or anything like that. All I did was put in some different values where we get a min and a max. If our min comes out to be something with an I, that means this thing is going to be safe at any minimum speed. We can be 0 and we will still stay put. If we get actual values, then we get some kind of a range that we have to worry about. I would go back and just change the beginning of this to be these values so that the whole problem works out, but it's actually a helpful thing, I think, to be able to see what happens if I do this thing and I get a negative number under my square root. Like, what do I do with that? Did physics break? No, it didn't. It's just saying there is no real minimum speed. 0 is enough. I do want to add in one more piece because it's worth adding. If I had this same situation that I've got and I wanted to look at the no friction case, having already formulated this out once, I could do that. I could say right here, let's let mu static be 0. That's what it means to have no friction. If mu static is 0, this whole term goes away, this whole term goes away, and I'm left with v equals the square root of g r. I'll have a sine theta over cos theta. That is a tan theta. And that matches up with exactly what I had before. So I can do this problem once. If I'm faced with a problem like this, I can do this problem once using friction, like leave friction in there. I can switch from maximum to minimum by just changing the sign on mu, and I can switch that to the no friction case by just plugging in mu equals 0.